Dear students, welcome you all to the econometric methods course. In the last few modules, we saw how distributed lag models are estimated. We saw the ad hoc method and a priori restriction method are used to estimate the distributed lag models. In the a priori restriction method, the KOYCK approach was quite popular. Though the KOYCK approach to estimation seems algebraic, there are theoretical justifications for the same. Today, we are going to see how KOYCK's approach to estimate the distributed lag model is justified theoretically. Theoretical justifications are essentially drawn from models of expectations. These models of expectations involve expected or long run variables. For example, production depends on expected sales, investment depends on expected profits, demand for money depends on rate of interest. In practice, there are different approaches to models of expectations. We are going to see the adaptive expectations model and adjusted stock models that justifies the KOYCK transformation. These models of expectations have got wide practical applications in econometrics. In today's module, we are going to discuss about adaptive expectations model. Let us see that today. Let me rationalize the KOYCK transformation. Let me explain that rationalization through the adaptive expectations model. This model was introduced by Kagan and Friedman. Kagan and Friedman takes up a simple model of demand for money as a function of expected interest rate. They form a model, this is the simple model, yt is equal to alpha plus beta xt plus ut. This is a very simple model. He takes up this model and he forms the he models the expected rate of interest. So, these together, actually this model is based on the expectations of some variable, and this expectation is further is modeled. So, let us see how it is done. According to Kagan and Friedman's approach, expectations are formed on the past experiences. The expectations of interest is based on the actual interest rates of the past. So, this is the simple expression of that. This is the expected interest rate and this is the actual interest rates, and you have the effects in different periods. The effects of the previous actual interest rate keep on diminishing. So, the effect is assumed to decline at the exponential rate. This is the usual KOYCK formulation of effect, declining effect and declining in the exponential rate. So, beta I is equal to beta 0 power beta 0 into lambda power I, where I varies from 1 to infinity, and lambda is between 0 and 1. Now, we may write the equation that the expectation of interest as beta 0 x t plus beta 0 lambda x t minus 1, beta 0 lambda square x t minus 2, based on this the declining exponential declining or the exponential decay of effects. So, if we take the x t minus 1 period equation of this, we will get this subtracting lambda into 2, lambda in the second equation. If you multiply this second equation by lambda and subtracting from the first equation, we get x t star minus lambda x t minus 1 star is equal to beta 0 x t. Actually, this kind of derivation we have already seen in the KOYCK transformation. So, you can refer the KOYCK transformation class. So, this is obtained, and if further if we take the long run impact as beta I is equal to and this this is nothing but beta 0 lambda power I, this is equal to beta 0 1 plus lambda square, etc. This is a geometric series, and if you sum it all, we will get beta 0 into 1 by 1 minus lambda. So, this expression you will get. So, if you take the total impact as 1, if you normalize the impact as 1, then this expression will give you one more identity, beta 0 is equal to 1 minus lambda. If you know if you substitute in the equation number 3, we get x t star minus lambda x t star minus 1 is equal to 1 minus lambda x t. If you add subtract x t minus 1 star, we get these two terms. These two terms are added and subtracted, and if you do some arithmetic manipulations, we get this expression. And this can be further reduced. Actually, this this can be combined, and you can get this expression x t minus x t star minus x t minus 1 star is equal to 1 minus lambda x t minus 1 star. So, this is famously called the adaptive expectations hypothesis. This is what is called adaptive expectations hypothesis. This hypothesis says revision in expectations are in proportion to the error in expectations. So, here this since lambda is between 0 and 1, 1 minus lambda is also between 0 and 1. If lambda is equal to 1, then there is no change in expectations. If lambda is equal to 0, there is complete adaptation to the expectations. So, this is how the expression is interpreted. Okay, so this is what is already explained. This model implies that about interest rates are revised each period by a fraction lambda of the discrepancy between rate of interest observed in the current period and its expected value in the previous period. So, we have already modeled this expected term, and we have based on this expected the expectation model, we derived the adaptive expectations hypothesis, and we are going to substitute that adaptive expectations hypothesis into this model. So, this can be obtained. Actually, this has to be removed. Actually, in fact, this cannot be observed in practice, and when you tend to remove, we certainly will use the adaptive expectations hypothesis equation. Okay, now to do that, we are having this original equation, and we are going to write the lag equation of this original, and we are going to multiply that lag equation by lambda, and we get this, and we are going to subtract this 5 and 6. So, if we subtract this, the expression you will get this is this one. This is y t minus lambda y t minus 1 is equal to 1 minus lambda alpha plus beta x t star minus lambda x t minus 1 star plus u t minus lambda u t minus 1. Okay. So, this can be derived. Actually, this the value of this could be derived from the adaptive expectations hypothesis. We get 1 minus lambda x t plus v t, where v t is nothing but u t minus lambda u t minus 1, because this is what we have actually this term is replaced with v t. Okay. So, this the value of this is nothing but beta 0, this is we already seen beta 0 x t, that is equal to 1 minus lambda x t, because this 1 minus lambda is obtained from the total impact is normalized. So, this is the expression we replace here. So, this expression is replaced for this one. So, you get this equation. Now, let us see the equation. So, this is the form. This is very similar to the one we saw in the KOYCK transformation. You have the AR term, but it is derived from theory straight away. We derived from the adaptive expectations hypothesis. So, an equation comparable to the one derived from the KOYCK transformation, the adaptive expectation hypothesis implies a structure similar to the KOYCK model, and hence it is taken to give rationalization to the KOYCK formulation, which is otherwise an atheoretic formulation. So, this may be written as that equation may be written as alpha dash equal to lambda yt minus 1 plus beta dash xt plus vt, where alpha dash is 1 minus lambda alpha, beta dash is 1 minus lambda beta. So, this is a typical equation. This equation may be estimated with the usual data set, but this as we discussed earlier, this may have two problems. One is this has a close relationship with this Vt is autocorrelated, that we discussed. Vt is nothing but ut minus lambda ut minus 1. So, even if ut is not autocorrelated, this Vt would surely be autocorrelated. That is one problem. Second problem is this yt minus 1 and the ut minus 1 in the Vt may be related. So, it may lead to biased estimator of lambda. So, these two things have to be corrected. If these two things can be corrected, then we can estimate the values of alpha and beta of the original model, the this adaptive expectations model, the original model. This yt, otherwise the demand for money, is a function of the expected interest rate. So, the demand for money as a function of the expected interest rate, which is unobservable, can be estimated. This alpha and beta can be estimated with the help of alpha dash and beta dash, because alpha is nothing but alpha dash divided by 1 minus lambda, and beta is nothing but beta dash by 1 minus lambda, and lambda can be estimated from the coefficient of yt minus 1 in this equation, this KOYCK regression model. So, alpha dash and beta dash can help you estimate alpha and beta. The standard errors of alpha and beta may also be estimated from the standard errors of alpha dash and beta dash. So, from this we can estimate the actual regression yt on the expectations. So, the expectation model can be estimated from the KOYCK equation. So, this provides another interesting application of this adaptive expectations model. The coefficient beta dash, otherwise 1 minus lambda beta, measures the response in y due to xt, while the coefficient beta measures the response in y due to xt star, that is the expected long run interest rate, expected or long run interest rate. So, we can estimate the effect of short run and long run interest rate, long run and short run interest rate on the demand for money. And also 1 minus lambda measures the coefficient of adjustment. So, with this the formulation, we can estimate the long run effects and short run effects and the rate of adjustment of the convergence between the long run and short run coefficients. Now, let us take one example from the basic econometrics book of Gujarati. Here we have given the example of short run and long run consumption function estimation. So, this is the original expectations model of expectation. This is CT hat as a function of xt star. This is a consumption function. Consumption is regressed on the expected or permanent income. So, this cannot be straight away estimated. This we estimate through our KOYCK equation. So, this KOYCK equation is CT hat minus alpha plus alpha dash plus beta dash xt plus lambda CT minus 1. So, once this is estimated, we find the R squared is very high, and so the model is best fit and the model is significant, and now we see the coefficients are also very significant, and this is lambda. From this lambda we can find 1 minus lambda, which is the adjustment coefficient. So, that is found to be 0.499. After finding this, we may estimate the long run consumption function. The original function can be recomputed, and this is the long run equation or the consumption function based on the permanent income. So, we get this coefficient is got from the short run coefficient just by dividing it by the coefficient of adjustment. This is 0.499. Actually, you divide 0.404 divided by 0.499, we get 0.810, and if you divide this 1038.4 divided by 0.499, we get 2081. So, this function, this long run consumption function is got. So, you have short run and long run consumption function. So, you have the short run and long run MPCs also. The results show the long run marginal propensity to consume is 0.81, which is double than the short run marginal propensity to consume. That is the one observation that we have we find here. The adjustment rate is 0.5, suggests that in any given time the consumer closing in towards the long run MPC by 50%. So, this adjustment is very high in this model. From this example, we learned that we can estimate the model of expectations, and this model of expectations could serve together with the KOYCK equation the long run and short run functions or versions of the same function. So, we can interpret the coefficients also. So, it is quite useful in practice. So, the KOYCK equation is of great use theoretically and empirically. Now, let us summarize what we have learnt in the module. Today, we rationalized the KOYCK transformation using adaptive expectations model. The adaptive expectations model helps to handle unobserved or expected variables in the right hand side. The model of expectation together with KOYCK's equation helps to estimate the long term and short term coefficients, which has practical applications in consumption function. I hope you have enjoyed this session. Thank you for watching.